So greetings students, we will be next moving to your DC series motor. So as I said, your construction of the classification of your DC motors will be based upon your armature winding and your field winding. Okay, so here in your series motor, your field winding will be connected in series to that of your armature winding. Okay, so what happens is that the resistance of the series field winding will be very much less. So but in case of your shunt motor, what you have seen was your shunt field winding will be very higher than that of your armature winding. But in case of your armature series motor, what happens is that your RS, that is your series field winding, will be very less compared to your RA. This is happens why in the sense means in order to uh, reduce the limitation of the flow of current. That is, your current has to flow, right? In the series, excess amount of current has to flow. So for that purpose only, your RS will be very minimum when compared to your RA. So here the flux produced is proportional to that of the field current. So here what happens is that if phi will be directly proportional to IA. But in the case of your shunt motor, your phi was a constant. But over here, this will be directly proportional to your IA. Okay. So here this happens why, because the field current IF will be equal to IA, because here there's a, it is not in parallel and there's not any type of parallel connections or the node. So what happens is that the current flow will be directly will be like this, phi equal to phi will be directly proportional to IA. The flux can never become constant in DC series motor. Okay. So but in case of a shunt, it was constant. So that's the main difference. Okay. As the load changes, IF and IA also gets changed. Okay. Coming to the torque and speed equation, the same thing. This is from your DC motor concept. So here your IF will be equal to IA. At the same time, your phi will be directly proportional to IA. So what happens is that the substituting means your torque will be IA square times of T. Okay, so as it is IA square times of T, what happens? You have to start your DC motor with load. So DC series motor with load. This is an important criteria. This is a very important criteria. They will be asking in 2 marks frequently why you have to start your DC motor with respect with load. Okay, because of this IA square parameter. Now you have to substitute your V. Okay, so here the 5 terms comes out. Y means but in the previous case of a shunt motor it was a constant, so we omitted it. But now minus IA RA minus IS RS. So this is what, as this is in series. Okay, so finally you will be getting this thing, and your IA and IS will be equal because it is in the same loop. If you are applying KVL means it is in the same loop. So IA and IS will be equal. So next we'll be seeing about the characteristics. As I said, the characteristics will be given by these three main waveforms. Sorry, graphs. Okay. So now your T will be directly proportional to phi into IA, and phi will be directly proportional to IA. So this you have seen in your torque equation. This also you have seen how this happens. Okay. So what happens is that when IA is large, phi remains constant due to saturation. That is, the flux will be varying, but when your armature current is large, when IA is large, okay, when IA is large means your resistance must be low, RA must be low. Okay, RA must be low. When your IA tends to be large, your phi increases, and after sometimes it becomes a constant. Okay, so hence this IA value will become a IA. So IA square becomes a IA. So here you can see this is what I have been talking about. Up to some particular period, it will be increasing in an exponential format. So after that, this becomes out to be a linear pattern. Okay, so here you can see the difference between your shunt and your series motors. Okay, so this is the main part. Okay, so up to this will be your TA will be directly proportional to IA square, but after the particular saturation point, your T will be directly proportional to your IA. Okay, next is about your speed versus armature current. So here we have seen about your this we have seen in the torque equation. Okay, in DC series motor, the field exciting current is equal to your armature current. Okay, which is nothing but your load current. Therefore, at light load, when saturation is not attained, so when the saturation is not attained means it will be under this criteria. Okay, the flux will be proportional to your armature current. Okay, that is your flux will be proportional to the armature current. Phi will be directly proportional to IA, and hence the speed will be inversely proportional to your armature current 1 by n. Okay, this is what they're saying. Hence the speed and the armature current characteristics will be looking like this, like a hyperbola. Okay, as the load increases, the armature current also increases, and the field gets saturated. Once the field gets saturated, the flux will constant. So now I think you are clear. As your load, if you are increasing your load, the armature current increases, right? So as your armature current increases, your characteristics will be attaining your saturation point. So after saturation point, it will be of your constant. Flux will be of your constant. Next is the speed versus torque characteristics. It will be more or less the same because your IA is again directly proportional to your flux. Okay. So some of the applications of your DC series motor include your you need to start the motor with respect to your load. So it will be like traction, hoist and lifts, like crane, rolling wheels and conveyors. So these are some of your applications of your DC series motor. So thank you.